Well, we've got a great program. Joe's gonna show us how he's using the spectrograph to analyze something, and that should be very, very interesting. Hopefully we'll all learn something there. Also, what was it, Monday, Phil, that we had, was it last Monday or this? It was last Monday, right? Not, we had the Crow family come out. There was 4 granddaughters, and they really enjoyed it. They were great people. We showed them around. Unfortunately, the sky was playing serious peekaboo, so we couldn't look through the RJ. We had one opportunity, but it was gone in a flash. And they did send us a video that they made out there. They took some pictures, and they really had a good time. So let me see if I can I share that? If you don't mind, I'll share the video. Hold on.
Sure.
You may tell who they are, Julie. I was not aware who they were until Ed explained it to me.
Yeah. Uh-oh. I'm doing something wrong here. I didn't hit share. Let me go back. Oh, man. I got to go back out again. All right. Share screen. Screen. Share. Am I sharing yet?
Yep.
All right.
Yeah, there you go.
Jeez.
Wow.
Got enough icons?
I know, icon and attic or whatever. Uh-oh, what happened to my damn? All right, excuse my French. Hold on, I got to go back in. I seem to lost the video here. Gotta find out where they are in there. I need to delete some more emails, don't I?
Yeah.
Let me search for the crow. Oh, here they meaning Christine Crow Brennan, Patty Crow Keller, Phyllis Crow Andrews, and Paula Crow. They sent us a video that they made, or one of them made. So here we go.
All right.
Download. Well, I don't know why it's doing that. Open.
Oh, kind of cool. Cool.
Yeah. So they really enjoyed that. Let's see. All right. So let me turn off my share if I can figure out that. Stop share. All right. So I thought that was pretty good. They sent us a video and they showed us some of their stuff. We showed them some of our stuff, and they had a great time. Very, very nice people. And maybe they'll come back and see us when the sky's clear. So we tried.
Awesome.
Can you explain who they are?
Yeah, they're the telescope is Harnfigger Crow, and their grandfather was a big guy into making that telescope. And they found us, and they were really thrilled and shocked to see that his telescope was in the, they found out about our observatory, and they saw it standing there and doing its thing, except we had a milky sky. The whole sky was clouded. But when they left, they stayed quite a while.
I just got a video.
Pardon me? Was there a comment?
No, continue.
No.
Oh, okay. Yeah, so they did that video, and they might send us some of his notes, Mr. Crow. Maurice Crow, I guess it was, right?
Right.
Okay. All righty. So anybody have any observing reports or anything?
Of course.
I have a solar observing report.
Go ahead, Joe.
Last Saturday, I had the my 80mm lunt out, and recently got a hold of a camera, and the camera and a very prominent prominence could be seen on the sun. So I quickly put it all together and took a couple shots. I'm going to try to share that just to practice getting the screen share thing going. I can see that's not working. Where did it go? Select a window. Oh boy. How about that one?
You're sharing.
You see a solar image?
Yes.
Yes.
Yeah. So it's a composite that Phil put together,
Wow.
and this prominence right here up on the left looks like an ear. That was really huge, and you could see a lot of the kind of vein, work inside of the prominence.
Inside that prominence.
Is it upside down?
No,
No, looks
Okay.
good.
And then there was another prominence over here on the upper right, another little horn that actually has sort of a hole in the middle of it that you can just barely see. I don't think
Mhm.
zooming it in would do much good. But yeah, you maybe see it a little bit better there. In
Right.
addition, which is really hard to see on the screen I'm looking at, there's a bunch of filaments that are on here, and plage, a couple plage areas. No sunspots, unfortunately. But I thought for an unguided second attempt at solar photography, I thought that actually came out quite nicely.
Joe, that bright ring around the exterior, I noticed after Phil had done his magic, is that real or is that some artifact?
Well, I kind of suspect it's an artifact, but we could
Artifact.
call it the specula.
It's,
There is a light ring of
yeah,
little pointy
you do the
tongues of
HDR
fire that come out of the
conversion.
sun like that. So we could call it that. I'm not really sure. I suspect it's an artifact though.
Yeah, it's an artifact. I've processed a lot of that, and it's just something that happens in the curve window when you try to invert the surface to get the background still black.
Yeah.
It kind of snaps really sharp, and it'll make that little ring. But I think it's actually very pretty, so I usually leave it in.
I fooled with it, tried to
defines it as a
reproduce
ball.
Phil's work, but I couldn't do it directly. So thank you very much, Phil. But I thought they were very impressive prominences, and since it's one of the few openings that we've had recently, I'm glad I got out there and gave it a try.
they were still there this morning, according to spaceweather.com, at least the big one, the fan.
Yeah.
It's gone on for 3 or 4 days now,
Hmm.
which is a huge amount of time for that.
Well, they're typically related to filaments, and filaments can go on for months. The thing is that they're rotating, right? So that there are features on the surface, and they just happen to be on the limb, silhouetted against against space. So that's why we get to see them. And as the sun rotates, they'll tend to either come onto the face or go behind what we can see. So it could be there for a few days, and it should get closer to the limb as it rotates. Whichever way it's supposed to be going from that side.
Very nice, Joe.
Yeah.
Hey, I
I
forgot to,
got
oh, go ahead,
something.
go ahead.
So I have. Well, I don't know if anyone saw the image that I had done of M27 at StarQuest at the public night, the first public night. Because I was imaging on, I would say, on the pad, and I was showing everyone like the previews. But did anyone see the final?
No,
No.
No.
Well, let's try and do this. I bomb this every time, so
Yeah.
give me a minute. There it is. That's the one. And share. Everyone sees
Okay.
it.
Yes.
Oh, yeah.
So
Wow.
I really
Wow.
liked it. So it's really cool that you can actually see the obviously it's a planetary nebula, but you can really actually see the structural details
Wow.
here, like the nodes, you can see that it has shape,
Yeah.
almost like like a peanut. It is almost kind of what it looks like, or a cashew, walnut, whatever. And then the Dumbo ears are very prominent.
What size of scope was that, Dan?
130.
Wow. That's awesome.
Yep, I really like that one. And then the following night, because it was clear for like 3 nights in a row.
Right.
And so the next night I did not go to StarQuest, but I did stay here. I set it all up at the backyard.
Yeah.
And I just automated it and went to bed. And
Yeah.
this one.
Oh, yeah.
Wow,
Wow.
Wow.
That was taken from home
that's pretty darn spectacular.
in my sleep.
Yeah.
You're working too hard on that.
Yeah.
Yeah, really, absolutely. My goal, excuse me, my goal, which I really set out, like I genuinely, I really 100% did not want to give up on it until this right here. If you can see where I'm guiding along, that is the actual explosion layer or supernova hydrogen shock layer
Wow.
from the original star that has created
Oh,
this
yeah.
loop. And that it's so faint. It's so faint because it's so thin and it just goes right along. And you can actually see it kind of swiggles right here.
Yeah.
And it's, oh my God, it's so faint. You can barely see it, but you can see that there's like there's a glow. You can definitely make out a significant hydrogen
Yeah.
glow around it. That was
Wow.
cool.
Dan, what is that, Dan? Is that a piece of the veil?
Yep.
Yeah,
It's
the network.
Yeah, it's
Wow.
the veil. Really like that one. And then the last one, this one was purely taken. Actually, this was StarQuest, but I don't know what I did. I either loosened a bolt that I shouldn't have, tightened the wrong one, then was like, oh, I shouldn't have tightened that one, and then loosened the wrong one or whatever. But my focuser didn't work for the first hour, and then some combination of me tightening bolts made it work again. And but either way, I lost an hour of data. Buzz this one, and yeah, it doesn't look. It looks okay, but yeah,
Oh, that's pretty
and
good to me.
it's an area in Cygnus. Excuse me, but it's got a nice little planetary nebula up here. Nice, beautiful little region. You got a star cluster here, which is nice. And then you kind of see some hydrogen tufts and things. And this is presented in HA RGB, so it's true-ish color. So it essentially looks kind of like how it would if you had giant eyes.
Wow.
Nice.
And that's all. That's all I got.
Very impressive.
Okay. Yeah, I
Thank you.
forgot to mention that we had a pretty good sky out there Saturday. And how many people? We had over 20, didn't we? Somebody?
Oh, maybe 25 or 30. I don't know. Exactly.
Yeah, we had a decent crowd, and we had like Peter brought his scope, and Ed had his scope, dazzle them on the pads, and then we had the 16 and then the RC, the Crow one, and then we're having little problems with the other one, so we're
the 12.
investigating that. The 12 kind of died on us.
Yeah, and we had
I
a
don't know with that one.
We'll find out soon.
We'll find out. We had to, Phil and I took us a while. We tried to take the faceplate off, and I got 3 of the screws out, and one of them, they were down so tight, and one of them we had to use the easy out to get it out, and then we pulled the panel out, and you don't have much room to pull the panel out, so we got frustrated and hung it up for the day. You can't. So we'll have to come back at it again. So.
Julie, don't forget to mention the world-class meteorite we had out there.
Oh, yeah. Why don't you talk about it, Ed? Go ahead.
Okay, well, it was the best I've seen in my lifetime, and I'm starting to get fairly old. It was huge. I don't know, Joe called it out first, whatever like that, but it seemed very slow and very bright. And it finally broke up in about 4 or 5 pieces that I counted, whatever like that, and they all burned up. But the amazing thing that I saw was that it actually brightened the ground. It was so bright
Yeah.
that the grass actually came, it was like somebody was shining a flashlight from like 50 feet behind you on the grass, whatever like that. So it was several magnitudes brighter. And like I say, that's the best I've ever seen. It was north to south and just east of the observatory from where we were standing there. And the nice thing was a good part of the crowd out there all saw it too. So the 25 people or 20 people we had out there actually saw it. And I don't know what the magnitude was, but there was one posted on space weather from the day before out in Oregon. And they had one down there. They said that it was a magnitude 6, which looks similar to ours. But what I didn't understand was it said it was basically like a golf ball sized piece of rock. And I don't know, maybe Ben is willing to give us some chemistry or physics on this thing there, but how a thing the size of a golf ball could create that much light. I mean, that's almost like a nuclear explosion of a rock, isn't it?
So, I mean, yeah, Ben,
I'll
chime
see.
in, but I could go too. Go for it.
Did it leave a trail?
Rock, paper, scissors.
Yeah, and it was a beautiful green color.
Well, plasma. So I mean, essentially it's very, very hot. And so very bright. Very fast. Very, I mean, easily orbital plus. So 18,000 plus at least. And a lot of times it's the shock front. It's the actual molecules of air not hitting the rock, but it's the molecules of air that are bunching up essentially in front of the rock that are getting very, 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 very hot, which are then heating the rock up, and then everything melts and all that plasma and rock that's bright as hell.
Yeah,
That's cool that you saw that. I have, yeah, that's really cool. I haven't ever seen anything like that.
Does anybody remember the time? I think it was around 10:30, wasn't it?
could be.
I- I guess I managed to miss that, Ed. You were talking about it.
Oh, it was.
Did you hear the whoos and hows and everybody was said, ooh, I mean, it got everybody's attention.
Kind
You
of
were
almost
the other
looked like a green basketball coming down. I mean, it was big. Maybe I'm exaggerating, but I've never
A
seen
little.
it like that before.
Was it on that sky thing?
On what's
Like on the report, or if there was like a, tracking fireballs?
That's it.
Didn't,
There's usually like a NOAA report.
Oh,
no, we
I'll have to check that out.
yeah,
Okay, I don't know. I
Baseball.
didn't. I wasn't sure.
yeah.
yeah.
Anything else before we go on to the program? I guess it's 8 o'clock and we're moving right along. Been some great showing here tonight. I appreciate all that. And Joe, you want to start? Are you ready?
bet. You bet.
Take her away, Joe.
Thanks. Thanks, everybody. Hello. Let's see if I can figure out which one of these applications I'm supposed to be. Is it this one? No.
You're sharing.
Yeah, that's not the right one, though.
Oh,
Let's try that one. Anyway, as Julie said, look at an application of a spectrograph that's a little bit off. Do you see something that says, please move this window?
Yes,
How
yeah.
do I get rid of that?
away from.
Away from what? Try moving the window and see if that message goes with it. I don't know.
Which window?
That orange thing.
I've never seen one of those.
There you
It's
go.
fading, but why does it come back?
I don't know. What is it trying to say? Away from something. That's all I can see. Huh.
Huh.
Well, I
I
guess
don't get it. Beats me. Did I stop sharing and try again?
I kind of like it.
Phil, you would. Try it again, Joe.
Oh, sorry about this.
No problem. Don't worry about it. Hang in there, Dick.
I'm trying.
Stuff that lung back down inside.
I smoked Lucky Strikes for 32 years.
Oh, you know, in my sea rats in the Army, I gave away all those little packs of Lucky Strikes in there.
Okay, you seeing my screen now?
Yeah, you're
Back to
good.
the start? All right. Anyway, like I was saying, that we're going to look at kind of an off-label application of the spectrograph. And it's kind of an interesting application, I think, because what it allows us to do is see what happens to light as it goes through one of our optical filters. And along the way, we'll take a look at the equipment that was used. We'll take a look at some of the parameters that go in defining the performance of a filter, and then we'll kind of sum it up and see what we've got. We looked at quite a few filters, but boiled it down to just 9. So that's the starting point. Hope you enjoy it, and let's get into it. I'll give you a little bit of background on. I'll try to give you. Oh God, here we go again. There we go. A little bit of background on me. I am a double E by degree. Went to good old Purdue and the Hammond campus. I've been involved in many different kinds of projects over my career. A lot of them involved RF. A lot of them involved radios. And so, being on the design side, you have to do a lot of testing. One of my other hobbies is radio, amateur radio. I'm a licensed amateur radio guy, and I've been in astronomy basically since the comet, so since about '86. That seems like it's about 35 years. So what does all that have to do with what we're doing here? Well, as an RF test person, and Julie can back me up on this, one of the major pieces of test equipment that we use is a spectrum analyzer. What the heck's a spectrum analyzer? Well, that's a spectrum analyzer right here up in the upper left. And a spectrum analyzer is very similar to a spectrograph. But if you're not familiar with either of them, then maybe this picture will do us a little bit of good. The spectrum analyzer allows you to take a look at what an RF signal looks like and all the component frequencies that go into it. And it takes that information and puts it up on a screen for you. And so each one of these lines here represents an active frequency in the signal that you're looking at. So anything like this this dark space right here, oops, dang it, getting out of sequence. It shows you that there's an absence of energy there, which is very similar to the way a spectrograph works. Now with a spectrum analyzer and just the basic display, you can see things like what the passband of a filter like device is, like this RF bandpass filter that we've got hooked up in a test mode down here. We can see what the passband is from one of the basically zero response points to the other side of the zero response point. We can see what the active bandwidth is, and the bandwidth is defined as like halfway up the curve here. So from the halfway point on this side to this side, that defines the active bandwidth of the device. And if you know what the energy going in is, you can measure the energy coming out, and you can find out what either the transmission characteristic of it is, the percent transmission, or as is usually talked about in the RF side, you talk about attenuation. So I picked out passband filter for the example test system here for a couple of reasons. One was to show that a spectrum analyzer can be used not only to look at its sources, you know, like radio transmitters, WOWO, digital TV, radar, what have you, but it can also be used to evaluate RF components or RF subsystems. And a filter is both a component and a subsystem. And when you test something like that, you have to have a source of energy. And that's usually provided by the spectrum analyzer itself with something called a tracking generator. So the energy from the spectrum analyzer goes out its RF port and into the device under test, the unit under test, the UUT. And then the response of the filter is measured at this end and then is displayed up on the screen. And those things that I had mentioned, including, I should mention, the center frequency, but the bandwidth, the attenuation or transmission characteristic, all can be measured. Now, these days, with all the computing power that's available, the spectrum analyzer is able to either compute most of these and a lot more things that are really not necessary to go into this evening because they don't have any bearing on optical filters. But they can also send the information out to a PC, and you can use the analysis software that comes with it to provide a lot of information that wouldn't be practical to fit on an individual screen. And you can print all this out and save it. So you've got an analysis package here. And so the test system that we're going to be looking at is going to be configured very similar to this. So you really want to keep this relatively simple design in mind as we go through it. We have an analysis tool, the spectrum analyzer. We have to have a source, and we have to have an analysis package. So when I think or hear spectrum analyzer, I immediately get the idea that we can use it in place of not in addition to, but as a spectroscope. So spectroscope and spectrum analyzer can be kind of used interchangeably for what we're talking about tonight. And then the type of filters that we're talking about, they're all bandpass filters. Bandpass filter is something like you see here. It only allows a chunk of the spectrum to get through, and then it rejects everything else. So that's very much like our OIII, our H betas, H alphas, and our SI1 filters that we use for visual and photographic purposes. It's also very similar to your sky glow and your ultra black filters like that. It just depends on what the bandwidth of the passband is. Depends what's being rejected. So when we think of passband filters, we can think of OIII filters or all of those types that I just mentioned. We can think of those interchangeably. So having that kind of background and knowing that we could put a system like this together, my thought was, why not test optical filters? It's just a matter of collecting all the pieces that are needed in order to provide a light source. So let's kind of take a look at the details on how this is going to work. So in addition to just wanting to test filters, because I have a couple of filters that date back to the early to mid 90s. So I have like an OIII filter that's around 25 years old and an H beta that's maybe just a little bit newer than that, but still, way over 20 years old. So how are they working? I've had some concerns over them. So with the opportunity to put together some test equipment to find out how they were performing, seemed like a good idea. But in addition to that, really what it amounts to is this whole project was just a really good opportunity to get hands-on time with the spectrograph, the LH high-res, without scope issues. And we've been fighting scope issues and continue to fight scope issues. Things early on like tracking and go-to and focusing, and now with the power problem that we ran into. So wanting to get some hands-on time with the spectrograph, be able to turn the micrometer and just get a feel for how you line up the cameras, everything that goes into using the spectrograph, sitting it on a bench and just being able to work with it. In addition, in order to evaluate these filters, had to take a step into learning the spectrographic software. There's a couple of those packages that are available. Vspec, the visual spec, and the real-time spec, RSpec, are available to us. I chose to use Vspec because, well, it was free and available to me, so I could download it and do all this analysis work at home. Considering the number of filters that we ended up looking at, I couldn't possibly go out. I would be living out at the observatory, and I didn't particularly want to do that. So learning the software, learning the workflow in order to get data about the filters really turns out to be very, very similar to what's needed in order to get data through the telescope from stars. So that actually worked out quite well as far as getting some hands-on experience with that. I don't really have an imaging background, in spite of the fact I've taken about six pictures of the sun now and some bad pictures of Saturn and Jupiter. But other than that, very, very slim exposure to the imaging side. So I'm trying to take all this one step at a time. And then, like I mentioned, the common testing common astronomy filters was just an excuse to take a look at some of my old filters and some of the other member filters that we'll look at in just a little while. So what we want to go into is the equipment needed to evaluate the optical filters. We need a spectrograph, which we happen to have. We need to have the cameras that plug into the spectrograph. We need a light source, and you can do it the hard way or the easy way. I'm not sure which is actually which at this point. The hard way is the expensive way, and you need a specialized piece of equipment that actually would give you a controlled light source that you could scan across the bandpass of each of the filters. But those are quite expensive. I think they're called monochronometers. That sounds like a clock, but I'm not sure that's right. Ben could pipe up and let me know if that's the right name.
Monochronometer.
Very good, thank you. Anyway, they probably cost as much as my house, and I didn't really want to put the club to that expense. So I went the inexpensive, easy way and use an incandescent bulb, a continuum source. And we'll actually get to take a look at that in just a little bit and talk about some of the pluses and minuses of that. I already mentioned the analysis tools, but it turns out that we need Excel, some sort of spreadsheet calculating tool to do a little point-by-point work. And we'll take a look at that as well. So what did we end up doing? Well, we did in fact use the identified workflow. We gathered some optical filter data responses using the spectrograph. Vspec and Excel were used in order to evaluate the data that was taken, and did find some interesting things along the way, some problems and some features, and we'll identify those as we go along. There we go. So this is just a kind of a spoiler alert here, let you know what we did see, what we did do in detail. 6 oxygen 3 filters provided by about 4 people. We looked at 3 hydrogen beta filters, and you'll see the results of all 9 of those filters in just a few minutes. We looked at many other filters. It's not that hard to take the data, as it turns out. It takes probably it's more intensive time-wise to do the analysis than it is to take the data. So it took a lot of data. Filters like a couple that I mentioned, Skyglow, Ultrablocks, looked at your basic color filters, so red, green, blue kind of filters. Those were kind of interesting. Also looked at some sources, including a fluorescent light that turned out to be a handy wavelength marker, and a couple of laser pointers. And we'll see 1 or 2 of those as we go along, but they won't be presented as major parts of what we're talking about tonight. So let's see. I found that the spectrograph, the cameras, and all the supporting hardware actually work really well. The workflow, as I mentioned, actually pretty much applies to the way you take stellar spectras. Found that exposure time and the wavelength sensitivity of the camera come into play on doing this work, and that'll be highlighted next. It's basically quantum efficiency per pixel at each of the wavelengths that the camera sees. And we'll go into that in just a little bit more detail. Vspec is a great tool. Found that neon calibration images for every micrometer change was a very good idea. Calibration can be done with a 10-point third-order equation, or a little simpler. It seemed with this particular project that worked really well. One of those things that allows is for this calibration equation to be saved and reused with any exposure that happens to be done at the same time, at the same setting for that micrometer setting. So every time you change the micrometer, you need to change a neon image, but you can use it across all the images that you take, no matter what they are or how many there are. So that's a real time saver. I mentioned issues with the 60-watt bulb. We'll see that. And the fluorescent tube and the laser pointer. So all in all, I think it was a really good project. So let's see what we actually did. Let's just get into that right now. So keep in mind the original opening slide there with the spectrum analyzer. This is the block diagram of what was set up. So the 3 major parts that you need are the light sources. I mentioned the 60-watt incandescent bulb. And that's our sun source. I used a fluorescent tube as a reference, and that turned out to be handy. There's a green doublet in there that allowed me to set the micrometer without having to do extensive back and forth measurements with the neon bulb, and then try to calibrate it and that sort of thing. So it turned out to be just a real handy marker without having to do a lot of calibration work with it. So the incandescent source, the continuum source, illuminates our filter under test. The filters under test were, if they were 2-inch, they were actually physically held in front of the eyepiece. That may or may not present some problems. I ran into a website that said that if the light coming into the filter isn't exactly directly into the filter, it could cause some problems with the center frequency and the response of the filter. So I tried to keep that squared up as best as possible. If they're 1 1/4 variety, then they just go in the back of the eyepiece, and then a diagonal to bring the light into the spectrograph. The whole point of using an eyepiece was to create a diffuse cone of light going in there, so that you didn't have to worry about focusing light or trying to put focus light specifically on the slit. The slit in our spectrograph is about 25 microns. It's not real big. So using a desk lamp like that, it seemed like there should be enough light in order to illuminate the entire slit plate, actually, without having to worry about focusing or anything like that. So that's the reason for the eyepiece and the diagonal. The grating that's used was the grating that's been in there for a while, 600 line per millimeter grating. The 694 camera was controlled by the data acquisition PC using SharpCap, and Excel was our back-end tool. So that's our spectrograph and data acquisition system. Did I miss any of my points here? No, we talked about one of the, well, yeah, of course, one of the best features of our spectrograph is that it's available. And so that was one of the major reasons for using the LH high-res. We've got it. Let's see, in the data X system, it's available and it has lots of hard drive space. So it easily accommodated all the images and supported all the required software. It normally does run SharpCap. So that's the background, that's the block diagram for the system. Physically, what it looks like is this. We've got our incandescent source over here, and just a clip-on light fixture. This is the sophisticated fluorescent reference that I mentioned. The spectrograph is set about 2 feet away. You got the data acquisition and camera control PC here. So if you haven't seen the spectrograph, it's got 2 camera ports. It's got a guide port and a sensor port. This is the H694 camera here. See the 25 millimeter eyepiece in the diagonal here. Another view of the, this has the fluorescent tube on. And then the all-important micrometer for setting the bandwidth, the range of light that you're going to be looking at with the sensor camera is right here. So you have to learn how to manipulate a metric micrometer. By the way, if you have any questions or comments, just pipe up. No need to wait to the end, but you can. So going from the physical setup, the workflow turns out to be, this is a simplified workflow, but it's pretty straightforward. Set up all the hardware, set the micrometer for the wavelength range that you're going to be testing, get calibration images for the neon, from the neon tube, and in fact, we need a calibration image of the incandescent bulb. We need to know what the intensity is of the light at each of the frequencies, each of the wavelengths of interest for each of the filters that we're using. So we have to do that. And let's see, and then just make the filter performance measurements with the light incandescent bulb through the filter. And the back end work is using Vspec. SharpCap will put out file formats, FITS or PNG, but Vspec only takes FITS and BMP, and I thought there would be a size advantage to taking them in PNG, so I had to convert them to all BMP so that I could use the Vspec. RSpec will take either FITS or PNG formats, so that's more convenient, but travel time involved is not convenient. So then you create your calibration file from the neon bulb. You create your filter response file, this specification file, the SPC, and then you wavelength calibrate them. You then create a response filter file in the DAT format, which is a data file that has the intensity and wavelength in a comma-separated variable format so that Excel could analyze it. And we need that. We need that to account for some of the characteristics of the incandescent bulb that was used. And then using Excel, you can analyze the performance of each of the filters. So that's the workflow that was followed. And following the workflow, we set the micrometer. Now I mentioned the ease of setting the micrometer using the fluorescent tube. It has 3 lines that are very handy for this. The 2 of the 3 that make it the handiest are this green doublet right here. And I found that by putting the green doublet over on the right side of the range, and you could set it. This is basically what you're seeing, what you're looking at on the screen of the PC. By setting the doublet here, I could capture the H beta and O3 filters very easily on this side. This is the blue side, and then to get the red response, all I had to do was to crank over the micrometer until I saw the green doublet on this side of the image. And so the red response would be all over here. And if we had a H alpha or an SI1 filter, we could have seen the responses here. What we did see though was whether or not each of the filters tested passed anything on the red side, or if they had a complete stop band that didn't allow that. And it depends on the design of the filter. Some do and some don't. So that's how the micrometer was set up. This gives you kind of an early look at what the Vspec output looks like. And by the way, this note here that says laser, this was my green laser pointer. Since the spectroscope has that open eyepiece on it, it was easy to shine a laser pointer into it and see what a laser looked like. And as you could guess, a laser is really sharp. Supposed to be a single frequency light source, but in this case, since the light source, the laser pointer, was only about $3, I got two green frequencies out of this, so 2 for the price of 1. And it doesn't really hurt the performance under the stars when you point this at the sky. No one can really tell, but it is only supposed to be a single source and very sharp at that. So pushing on and through the workflow, we look at the calibration process, the neon bulb calibration process. You take a neon image, as we see here. This is with probably the micrometer setting for 4.04 millimeters. And then you compare it to a known source so that you can identify the wavelengths of each of these lines. Then you plug the wavelengths of known lines into the dispersion calculation, and you're able to line calibrate the raw image. And as I said, you can use either a 10-point list or go with a 2 or 3-point list for calibration purposes. I found that I could get about plus or minus 3 angstroms. That's not too bad. That's really a very small difference. And so that provide a very workable calibrated source. Next, calibrating getting a calibrated image of the incandescent light source. So this is a 60-watt bulb from just above the ultraviolet. This is the blue end. You see H beta here, and you see the light. Its output is mainly on the red side. We start to get into the infrared band over here. So I've marked off the hydrogen alpha and SI1, SI2, whichever that the band is there. and you start to see it level off. So these slopes that we see here cause us all sorts of problems in the evaluation of a filter. Ideally, what you want is something flat, totally flat across each of these filter band passes. If they're not flat, then the response of the filter is going to look wrong. But that can be worked around by using a point-by-point calculation. If you know what the intensity is at each of the points, each of the wavelengths going into the filter, you can use that to calculate the percent transmission. So rather than working in the intensity that you measure, you simply work in the percent transmission. So that simplifies and takes one of the problems with an incandescent bulb out. But you can see all of this infrared energy out at this end, and why a bulb gets really hot. Don't really know why we get this scallop effect on here. Not really sure why. I was expecting a smooth curve, but exactly why it's not smooth like this. It's kind of an interesting question, but one that I don't really care to go into. Might make a nice science fair project to investigate it. You know, maybe it's cooling, just the radiating and heating of the element, and maybe it has a hot cool cycle. Maybe it's related to the length of the filaments. I don't know. We could do a set of experiments or run a science fair project for someone. That would be okay, but not really sure. Well, I guess
absorption in the air.
Say again.
Maybe some absorption in the air.
Could be. It could be. Could be cycling kind of a hot and cold sort of a cycle over it. The other thing I thought perhaps that might have something to do with the 60 hertz power that's running this. Be interesting to plug in some DC on that and see if these bumps went away. Don't know. Kind of interesting. You run into interesting stuff every now and then.
Yeah.
This is interesting, but I don't really plan on pursuing it. So the bottom line here is incandescent bulbs are cheap, but they're not really ideal sources, but they sure are available still. Okay, this is a very busy slide. I apologize. It's kind of dense, but here we go. I'm going to take this in kind of a top left and rotate around through to the middle right as we go. So I talked about source intensity variations on that last slide, and I said that an ideal source would be flat. It would have the same intensity over the filter's wavelengths of interest, but it's not. And this is approximately the slope that we were seeing across the H beta range. So it's really not nearly ideal, and so it really forces that point-by-point calculation of the transmission percentage of the filter. Another thing that comes into play is the camera's spectral sensitivity, each pixel's sensitivity by wavelength. And this chart in the middle here does come from basically Starlight Express, and I found a couple of other places on the internet where this chart is reproduced in just about the same format. And so at 4,000 angstroms, you're down 40% from the peak of the response. And as you trail off, it actually gets much worse quickly. The camera is only rated to do about 3,600 on the ultraviolet side before the response basically goes to zero. And the fall off on the red side is not quite as bad. So you could do some near infrared work if you like. But at any rate, this causes us some problems too on the passband shape, on the filter shape. Now I really didn't. I did a few point-by-point measurements on here just to populate this graph, but I didn't attempt to reproduce this entire shape, this entire sensitivity response. Both Vspec and Rspec have methodologies that allow you to do this for stellar spectra. You use a calibrated star spectra of the same type that you're working with, and through the analysis capabilities that are in both packages, you can take out the system's response excuse me, in order to get a flat star spectrum. So I basically kind of ignored it. And that would be an area of improvement. If we were going to go into business and try to do this, we would probably have to account for this along with having some test standards. But for this exercise, I'm just mentioning it, and I wanted to identify how you would deal with the same problem if you were looking at a star spectrum. And maybe Ben has some thoughts on that, what he's done with this, but it's a standard process apparently. I'm just not real familiar with it. I've got just the basics of using Vspec and RSpec at this point. Sorry about that. So anyway, if you take this this actual source and you combine it with the throughput of the percent transmission of the filter, you get this real sharp slope here, which is not the real characteristic of the filter. You're really looking for something like this. We've all seen these characteristics for the various filters. So this is very distorted because of the lack of an ideal source on the input side. Another thing you'd be looking at is the center frequency of where the line of interest is. In this case, you have H beta, which would be under the curve. Dang it! So this filter would at least be something that passed hydrogen beta, but your response at something like 60% isn't what you thought you were buying. So by doing a point-by-point calculation that I've mentioned a couple times, using the actual input value and the actual transmission intensity, you can then calculate each of these point by point. This is an Excel curve, an Excel graph that shows a more realistic characteristic curve for this particular filter. So from this, we can get the bandwidth plus or minus 50% point. We can see where the center frequency is. We can see where the actual filter line is, and then calculate an offset if we want to. But we can certainly get the actual percentage of the transmission at the filter. That's really what we want to do. That's what we want to get. So we know how the filter is performing. So why do I want to know the bandwidth? Why do I want to know what the plus or minus 50% points are right here? And that's obviously to keep out, if you have a narrower band pass right here, narrower bandwidth, the amount of sky glow you pick up from light pollution will be less. That's the obvious reason that the photographic filters are, 5 to 10 nanometers versus this, in this case, what am I proposing here? About an 80 angstrom bandwidth. So you get a lot more light pollution through in this case. So source intensity and pixel sensitivity are the two input variables you would deal with, and then deal with one of the two by the point by point. So that's the windup. And here we go. Let's look at some H beta filter characteristics, unless there are any deep questions on going through all that setup stuff. Okay. So the center wavelength of interest is 4860 for hydrogen beta. We're looking for bandwidths of about, narrower the better since this is a single line, but typically 30 to 50 according to each of these manufacturer characteristic curves. The red transmission varies, but they do some tricks with this. And the tricks that they go into this, if you look carefully, very carefully, since it's a small image, they only go up to the Lumicon and the Teleview only go up to 6,000 angstroms or 600 nanometers, whereas the Thousand Oaks, 600 is right here. And if you compare the Lumicon and the Teleview and the Thousand Oaks up to 600, you say, oh, Lumicon, they don't have a red response either, but they give you the characteristic up to 8,000 angstroms. So it does have a red response, but it's way up. So for visual purposes, I don't think this is a problem. And Gene mentioned old eyes and their exit pupil problems. Well, old eyes and red response, they're not real good high either. So it wouldn't really be a problem.
Joe?
Yes.
I was going to mention there, I looked up the old advertisement sheet on that filter, whatever like that, and that was designed on purpose to blocks red wavelengths normally passed by typical filters. Design eliminates star bloat to
Sure.
produce sharper, more natural looking stars. Anyways, that's their theory. So it's a design choice, I guess.
Yes, yes, it is. Yes, it is. I don't know that in the old days, like in the 90s, if they had that design choice, possibly, probably if there were specialized photographic filters. I personally have never really had a problem with star bloat with visual observing. So I think that's more of a photographic issue rather than a visual issue. So you got to know your application. Okay. So finally, some results. So based on the workflow and all of the issues that we just talked about, the results from the 3 hydrogen beta filters are presented here. I had 2 of them, and Ed kindly provided a test sample for one of them. And I wanted to crowd all of the blue end and the red end onto one chart. So it made all the pass bands look a little bit narrow. But let's kind of take a look at what we have here. So this filter that I've got right here, the JN1, the 1 1/4 H beta filter, this is like useless. You'll notice that the hydrogen beta line is right here, and this filter doesn't even come close to it. And in fact, when you go over to the red side, to the red response side, it turns out that it's not even close to the hydrogen alpha line either. So this filter is pretty much shot. And then you'll notice that the response is only about 50%. So half the light that goes in comes out. That's not very good for any filter. So about the only use I could think of for this filter into the future would be as a lunar filter, a moon filter, because the moon has lots of extra light, and it's always good to take the light down a little bit. But for any other use, it seems like it needs to be retired. Now, when I inspected that filter a while back, actually when I was doing the analysis, because I could hardly believe that it was down to like 50%, I noticed that there was a haze on the filter. I attempted to clean it with IPA. That's the isopropyl alcohol, not the India Pale Ale. It didn't come off. So I think that's a true aging characteristic. The filters have been, that filter and my others have been well cared for. They don't sit in a hot, humid environment. So if they did grow mold or something on them, it was just because of the time involved. And nothing came off when I attempted to clean it. My second hydrogen beta filter looks like it at least gets the line inside of under the curve. So that's good. But the response is just in the mid 70s at best on this. So at least it's workable as a hydrogen beta filter. It also has red response, but Ed's H beta filter wins. I mean, it's really good, but Ed could complain that, my goodness, it's only 85%, but I bought it and it was supposed to be 95 or 98. Well, I think there's some issues with another factor that was only lightly touched on or not mentioned. I think there was an exposure time problem. I didn't expose this long enough. So when I did some retesting, I found that if I use longer exposures, these response curves look a whole lot better. And by the way, Ed's filter had no response above 6,000 angstroms. It would be buried down here at the bottom. So his very good filter could be used for photography if he so chose. Maybe he bought it for photography. I don't recall asking him that. Ed, did you buy it for photography? No?
I bought it because I had money and they said I should buy it. But
There you
I'm
go.
mentioning that it's probably the newest design of the ones that you're testing here, because they came out this particular series here in 2018. So it's a fairly new production run.
Fair enough. So so that's the story. I've got a bad hydrogen beta filter that is retired. I tried it on the moon once. It doesn't look very good. So let's move on to the O3 filters. Now, O3 filters have to, in theory, they might accommodate 2 lines. There's 2 lines in the same neighborhood. There's a 4960 and a 5010 angstrom line. And so you'd really like to be able to accommodate that. And it looks like you need no less than 50 angstroms in order to get the two in there. And that would be a perfectly centered set of lines to get in under your filter curve. Probably want it longer than that for manufacturing purposes. I threw in the Celestron just for a little variety. It covers O3 and hydrogen alpha. So I guess this is another photographic filter, but you see the characteristics, which are very steep shoulders on all of these, and fairly narrow bandwidths. And then the Batter 3, this 10 nanometer, I suspect this is another filter that's meant for photography. And they claim no red transmission up to 700. So that issue with star bloating, you shouldn't have that with this filter or the Batter filter or the Celestron filter. So just an introduction, so you're familiar with the filter characteristics. On to an even busier, because this one has 6 filters, and guess whose filters these are? Oh, these are mine. These are my other old filters, and this one, the JN1 here, this one's another 50%er. This one I also examined and found a bit of haze on it. But it is interesting to see the high variability in the centers of each of these filters. They all at least hit the second O3 line, which is good, because this line, the O3 at 5006, is actually 3 times brighter than this one. So if you're only going to get one, you'd really like to have this one. And the percent transmission is lower than the spec, and I think that's just another effect of having underexposure. But since this was the first time we'd ever actually run this, the filter responses looked fairly good when we were looking at them live, and so the exploration of exposure times really didn't come until the back analysis part of it. So once again, Ed's filter wins. He's got the highest response and has the most area under the curve here for both lines. So he would have the brightest image going on this.
Is that a shallow view or something?
Yeah, I purposely didn't put the manufacturers on here in case we post this presentation somewhere. I didn't want to have any trouble legally, but Ed can answer that question. I don't have any problem with Ed answering.
I can answer it because I see it's being recorded there. I'm sure the manufacturer wouldn't care. It's actually made, both of them are made by Astronomic. Wow. It's a German company spelled with a K at the end, and they're resold or marketed through from Teleview. So I assume they're kind of like, well, we won't mention other companies.
Yeah.
All right, sorry I started that.
No, I just wanted to let you know why I didn't put the name, why I didn't put the manufacturer names. I put the owner's name, so
sure,
we'd have that discussion.
Okay,
but I didn't.
Fair enough.
I didn't want to go out there
Right.
and have any problems with that.
Sure.
Hey,
so
Joe.
Yes, Pete.
It's interesting the filter I supplied you does a good job on the second line and nothing on the first, and then that JN filter.
Yeah.
Whose was that? Oh, that's your filter.
That's my filter. This is my brother-in-law's filter. The PM
does
is
a good
Paul
job
Mara.
on the first line, but almost nothing on the second line.
Yeah. Don't take that too hard though. And the reason you'll see, I think on the next slide, that when you increase the exposure, these curves change dramatically. So in theory, all of these could have been redone, but I didn't want to do that either. So let's take a look at that. So the effect of running the exposure from 2 seconds to 4 seconds, you go from this filter response curve to this filter response curve.
Oh, wow.
That is an enormous difference. It almost invalidates everything we just looked at, but maybe it does. But it's the idea that counts here, not necessarily the actual percent transmission and the placement of each of the filters within the bandpass. But clearly you see there's a huge change. And the fact, and so you might think, well, gosh, maybe these are overexposed. The fact that we're only seeing like 80% on this filter. It indicates that we're not seeing 110%, for example. If we were overexposing, or if there were other problems related to a mismatch of the intensity of the light going in to coming out, we'd see some characteristics where the filter actually exceeded 100%. That would be nice to have a filter that actually produced more light that came in. And Ed actually has a system that does that, but it's not in the same price ballpark as an O3 filter, from Celestron. So it's an active device, and these are all passives. So anyway, I defend the 4-second time as being valid because there are no 110% readings here. There could also be something to do with the light coming into the filter at a more normal angle at 90 degrees coming in. There was in the website that I looked at, there was some discussion about how it could change filter characteristics. Maybe a little bit of that was in play. There's some variables that would need to be worked out if this were going to be run as a normal, service.
Hey, Joe.
Yeah.
When did you notice this characteristic on all of the filters, that longer exposures, you saw this effect?
Hang on a second. I'm going to fast forward to answer that question. Okay. So yes, is the short answer, but I'll just quickly click through those and see. So this is another one. This is the real bad H beta filter. It's really shifted, but the response curve came up 10% and it backfilled. So this is the O3 that we just looked at. There's another O3. Which one is run?
A little difference on that.
Yeah,
one.
this one is another bad one. This is my 1 1/4. This one has haze on it, and so I think this filter is just worn out over time. So it didn't have as big an impact on this filter. And then this one, that's pretty impressive difference. So it goes from barely catching or at the O3 1 line here, and now I catch both of them, and the response goes up a few percent, up into the mid 80s. So I think it's a dramatic difference, especially the width.
Joe, one other question. It's kind of like a two-part question. You never mentioned the term, and I was waiting for it, as double E, back when you introduced the spectrum analyzer and the tracking generator. That was a good analogy, but you never brought up the term normalization. And I think you probably would help people if you explained that. And the example of the incandescent bulb being not a true amplitude source across all wavelengths. What you tend to do is you want to normalize that trace, and so that you basically make it unity across all the wavelengths. So
I'm not sure how you would do that with a source that's actually so biased towards the red end and so low at the blue end. I mean, I think that's a true characteristic of the light bulb.
well, you're right, and that's what I'm saying. You had, and I think that's what you were saying you were doing when you said point to point. You were taking into account your
Right.
input. I think the process that you actually were performing, but you didn't mention the term, and I guess that's what I wanted clarification, is did you normalize your input source? In other words, make it unity to do your analysis. Because if you didn't normalize it, then these are not accurate.
Well, I normalized it in the sense that we did I did the point-by-point transmission calculation. So I used the actual input divided by the actual output rather than anything else.
Okay, so all right, so yeah, so that it sounds like you did do a normalization. But what puzzles me is why there is a difference with exposure time. If the input source has been normalized, then exposure time should be irrelevant. And I'm really scratching my head trying to figure out why there's this difference. Now, that has nothing to do with the angle of incidence, which definitely does affect the characteristic of these curves. If you are off the slightest bit, a half a degree, you can sway these results a whole bunch. So yes, you got to make sure you're pointing the light directly at it orthogonally. But that has nothing to do with the exposure time. So the fact that you were normalized, the exposure time shouldn't have made any difference. So I'm like you, I'm very, very puzzled why there's a difference with exposure time.
Yeah, I'm not really sure either. It could be, there could be some couple of effects.
Geddes, it almost looks like, look at that screen right there, that you're reaching some kind of saturation point around that 85%. And that if you went to an 8-second exposure, you would saturate all the way across the screen there.
That's possible, but what's significant about that graph is the shift. If you look at that blue curve, it's petering out at just under 5,000, and then the red one, is going well past 50-50. I mean, those are two completely different looking bandpass.
Yes, they are.
I don't think it's angle of incidence, personally. I think of our angle of incidence, we see an entire shift of the curves, but not necessarily a change in the bandpass. The bandpass seems to be completely different. So
right, and
that doesn't really, huh?
I was going to say, and that should not change based on exposure time.
No, you're right. My thought is maybe the stability of the light source is maybe the light. Joe, I don't know how many measurements you took. Maybe the source you're using, the light source itself, is not necessarily stable.
That's entirely possible. I think there are a number of items in here that would have to be picked through one at a time in order to figure out why the dramatic difference. Whether or not they're orthogonal. I think that I suspect that the bulb isn't very stable in terms of intensity over time, and that would have to be figured out. So it's this was a first pass effort. I don't mean to bail on my own.
Oh, no.
I know you're not, and I appreciate the discussion here. I think it's really good, and it just shows that what seems to be relatively simple is not. This is a fairly complicated, system that we've got here, and
absolutely,
there are a lot of subtle effects.
One thing you could do, Joe, is take this, for example, this particular filter, and do a sample of 10, test it 10 times, do an exposure of 2 seconds, and then do another one of 4 seconds or 5 seconds, and run that test 10 times, say over the course of a couple of hours. It would be fascinating to see the variation, if there was a difference in the intensity. And of course, if you're doing this correctly, you should be normalizing right before you do each test. You should not do one normalization. In other words, to do the point-to-point type thing, as you refer to it. You should be doing the normalization directly, exactly before you collect your data.
No argument. Without any hints of instability. I mean, the bulb wasn't flashing, for example. The assumption was that it was relatively stable, that it was stable over time, and so taking a calibration image of the light source wasn't done because it just didn't seem like it needed to. But now looking at results, and then you have to deal with what we have here and try to figure out how to isolate all of the effects that are going on. And that would be if this were set up as a as a service, to see whether or not, the filters you bought were correct and worked as they should. Doing something like taking a normalizing shot, a calibration shot of the light source would be absolutely required so that you had the best data possible.
I would be interested to see what a 6-second exposure brings up.
Hey, Joe, in our spec, they actually have a thing where you can look at the 0 to 256 and all the different pixels and stuff. I didn't know if did you calibrate out the camera's effect?
No,
Okay.
no. I don't know of a way to do that short of digitizing the quantum efficiency versus wavelength curve. And because both Vspec and RSpec have a better, easier way to do that, a more robust way to do that when you're looking at stars, I didn't really want to spend the time digitizing.
Understand.
Take out the effect of the camera.
Joe,
Well, you did a lot of work here. That's very nice.
yeah, Joe, you retired, didn't you? Sounds like everybody's
Yeah.
listen, they want to put you back to work.
Yeah, exactly.
Don't let them do
my
it.
answer to all of that is that, the student that we get that wants to come and learn all about, spectras and running spectrographs and taking stellar spectrographs, I think this would be really is a good hands-on project where each of these things could be isolated and, would be the point of the next person's investigations to get all this hands-on experience and all the experience doing the analyses.
All righty.
Oh my gosh, it's 9 o'clock. We're almost done. All right, where am I at? Okay, summary. Were the goals met? Yes, I think, as I just said, this is a great introductory project to the use of the spectroscope. Great introduction to the basics of Vspec or RSpec. As I mentioned a couple times earlier, the workflow directly applies to stellar spectra. I did find that 2 of my filters are kind of clunkers, but I suspected that, so that wasn't really a shock. Something has had a dramatic effect that we saw that makes my O3 filters look good. So I think it turns out to be a really good project. Lots of areas of improvement. If we were going to do this as a service, they would be needed. The hardware performed really well. Sitting on the bench, really had very few problems with anything. So I like that part of it. We just talked about many issues connected with the light source, but boy, it's available and it's very inexpensive, so can't beat it. And there are so many aspects of Vspec that need to be investigated. We just talked about another one, the ability to take out not only the camera's impact on the spectra, but the idea is to take out the entire optical train and its effect, which is another reason not to digitize the light curve. I looked and I only found I didn't find any digital versions of the camera's QE curve. I mean, there's various printed versions of it, but no one had a comma separated variable file that I could use to create a live version of it. And if there was, I could have taken out the camera's impacts, but very little gain from doing that as far as stellar spectras go, especially when the 2 analysis products will do that for you if you know how to do it. So anyway, detailed accomplishments. For some reason, looks like the exposure was important. You need to actually take out the camera's impacts. That's what the second is. The pixel sensitivity is very important and needs to be dealt with. In order to get around some of the bulb problems, ended up having to do the pixel level point by point intensity transmission calculations. 60-watt bulb probably does change wavelengths and intensities with time and its operating temperature and the ambient temperature. It turns out the fluorescent tube is a handy wavelength marker. That turned out really nicely. The laser pointers, I think, could also be used as wavelength markers under some circumstances. You'd have to identify that. as needing a calibration point or something, and then you could use them for that. But I don't really foresee that. So they're available, but not very useful at this point. You need to do, like they suggest, a neon calibration image every time you change the micrometer setting. It's just physically impossible to put the micrometer back exactly where it was. And for the purposes of evaluating filters, you might be able to get away with that. But if you're going to go into a stellar spectra and you want to actually identify lines, then fractions of an angstrom end up being important. So many different lines are piled up so close to each other that angstroms do count. So you have to be very precise on your calibrations. So I think my bottom line right here is that it's a very interesting project, but as we talked about, there are some areas that need to be improved and documented. So let's see. Good learning experience. And I'll just point out one thing. The Vspec calibrations, the wavelength calibrations, we're calling out a point 0.3662 angstrom per pixel resolution. And that's using the 600 line per millimeter grading. So I think a third of an angstrom is really good resolution for what we're doing. I mean, that's not considered ultra high or anything, but for what we've got, and we have finer gradings than that, that's, I thought, pretty surprising. The 5D camera resolution turns out to be about a half an angstrom, which is not bad, and it gives you a full, visual range of the spectra. So that's a handy thing. Still half an angstrom, not bad. Let's see. What else haven't we talked about here? Nothing. We're good there. Next steps. Remount the spectrograph and go after bright objects. I'd really like to get a spectra of Vega before it gets beyond the range of the 12-inch. I mean, we're going to lose it behind the shed pretty soon, behind the roof. So bright stars, bright nebulas, globular clusters, things like that. I think those are like next up on the menu. I personally think that the tracking and go-to issues that we saw earlier in the year have been resolved. So unfortunately, we have this other electrical problem to deal with, and once we get by that, we'll be able to do some bright stuff. I did want to look into the OIII filters to see where they, I'm not really sure what I meant by that. Oh, I wanted to retest the OIII filters to confirm that the center wavelengths were stable, but found that the exposure time seemed to be critical. We just looked at that in detail. I wanted to know whether or not, the next thing was to find out whether or not the brightness, which of the two lines was brighter. I thought that might actually make a good spectroscopic project to investigate the lines to see which one was brighter, but it was an easy internet lookup, and the 5007 line is 3 times brighter, I found. Also, to create a calibration library, it's good to know what the wavelength ranges are for the micrometer settings, and I've got a full set of micrometer settings from.
Hey guys, real quick.
Go
I
ahead.
gotta get running tonight, but it's been fantastic so far. I'm absolutely loving it. But I do have to get running. So you guys have a great night. Take care.
All right, Dan. You too.
Thank you, Dan.
Bye-bye.
And lastly, there are a number of projects that could be done with the spectrograph not mounted on a telescope, or if mounted on a telescope that's not tracking. If we wanted to, we could point this thing over at Fort Wayne and assess the intensity and what's in the light that we're seeing, how many mercury vapor lamps, that sort of thing. We could get the spectrum of our light pollution as well as its intensity. So that might be an interesting long-term study that could be done. We'd have to do a little bit of fabricating work to mount it on something other than a 12-inch. We just talked in detail about an incandescent bulb study to figure out how it varies over time and temperature, and what to do with whether or not to digitize the 694's QE versus wavelength graph to see if we were going to go in this direction of trying to do more detailed filter studies. We might want to do that. Not sure it's a good use of our time, but it's something that could be considered. So that's it. Open to questions. And my bottom line on this is, I'll say again, it was a great project and would be a great project for someone that was, trying to learn the spectrograph and the support software. That's it. Your spectrograph is being used.
Hey, Joe, if we had one of those old-fashioned variable resistors, you could change the voltage of that 60-watt bulb and see if temperature change made a difference in that graph of yours. I think that'd be kind of interesting.
I think it would be. It's just a question of how to use your time.
Right.
There are analysis issues that I haven't really properly figured out. Normalization is one of them. How to get the line spectra to look like some of the line spectras I've seen. How to take out the intensity values that are there, and bring that to one. Just using the tool to normalize the graph is one. Taking out the camera and the telescope response so that you get a more standardized look at the spectra. If you have a very deficient or a very low level, rather, blue side, everything that you get on the star spectra is going to look too low. And so to be able to take that out is important. And that's an area that I would rather spend time on rather than studying the 60-watt light bulb. It'd be a great science project.
Of course, the way you do that, Joe, when you normalize, you're just, if you go back to your spectrum analyzer example and you take the tracking generator output, if you plot that on the spectrum analyzer, of course, ideally you want a straight, perfectly horizontal line where the amplitude is not varying with respect to frequency. And because it's not perfect, it's going to vary up and down. So of course, the process of normalization is you divide that trace by itself.
Yes.
And anything divided by itself equals 1.
Right.
And therefore you've normalized it. And of course, you just keep track of what the divisor was in order to make it 1. And then that's applied to every signal that comes in, from that point on. So it really theoretically should be pretty easy to normalize all of your data and, before you collect it. Now, one other thought that I had, if you're going to do this in the future, rather than just using an incandescent bulb, which is, of course, that's why they get hot. They're almost pure, perfect infrared sources. Regular light bulbs are terrible at producing light. They produce more heat than anything. But what you could do is mix the two, use a fluorescent bulb and an incandescent bulb shining in, and the fluorescent bulb being rich in blue and higher frequency stuff mixed with the infrared and low rich incandescent bulb together would give you probably a pretty good starting point as opposed to just one or the other. Just a thought.
And I don't doubt that would be a good approach to try.
The problem with the fluorescent is it's so specific at certain wavelengths compared to the black box source that an incandescent light is. I was wondering, it's probably not possible to get an incandescent source that uses some other material for the filament. Originally, Edison worked with carbon, but that's probably not available any place. It'd be interesting to see different elements used in that.
I am so happy to hear that there is so much interest in investigating incandescent light bulbs and finding their strengths and weaknesses and identifying, why we've got this wiggle and that wiggle and how to get around them. I think that's actually I have a hard time not wanting to go in that direction myself. But as I said, I'd rather spend my time figuring out the details of using Vspec in order to get a good stellar spectrum, a good properly calibrated stellar spectrum. In principle, it looks easy, and I've tried it a couple of times, and it doesn't work out mechanically quite so easy. So that's what I would rather spend my time, and let somebody else. I'll help somebody else do that. I had my fun. I tested my filters.
Gene, you look like you got something on your mind there.
Yeah, well, what are you thinking about there, huh?
You unmute yourself, Gene, and go let it fly.
Pull a new bra there or something. I don't know.
That's an ugly brawl.
Yeah.
But I'm with you. I love the bulb. I love the problems. I think it would be really interesting to investigate it and find what's behind all this stuff. But I'd rather get the spectroscope back on the LX600 and point it at Vega.
Yeah.
This has been a very interesting program, but why don't we allow the public to join us in these meetings?
We're going to bring that up next board meeting.
Thank you.
We'll discuss the pros and cons and see if we can work something out, Dick. All right, Gene. You look like you're chomping over there.
I think, I don't know, is there a show of hands of anyone who wants to even bid on these?
I will
If we
bid.
were to start at like, $50.
Well,
I bid 50.
Jim already bid 75. I'm wondering if there should be an email mailing on this. We've only got 20. That's less than half of the registered members of the club.
Well, what I can do is I can publish it at the next eyepiece in a for sale. Give these binoculars to Phil Hudson to hold, and have them contact Phil. Highest bid.
Silent auction.
Yeah,
Silent
he could,
auction. Take your best shot, email it in.
yeah.
I think that's the best idea.
One suggestion, you might, if we could ever get the hardware to make it part of the observatory's inventory there to mount on that, what do you call that balanced binocular mount that we have, parabellum thing, whatever?
Parallelogram.
Well, we already have one.
Well, but we never use it. And I didn't know if you wanted to put that on that. We're missing a piece or two, but anyway, you could permanently mount that if you're saving the others for special purpose or something.
I don't know that we're saving it for special purpose. We already have one.
Those are what, 20 by 80s, I think. So
Yeah.
this would be great for the public to span the skies or whatever, like it, give them something to look at.
Yeah, whoever buys these, we would encourage them to come out and set up on a pad on Saturday nights.
all right. So are we going the email silent auction? Is that what everybody's pointing towards?
Yeah, I guess that's what we'll do.
All right. So be it.
Yeah, I don't know. Phil?
What do you got to say, Phil?
In the dark.
Yeah, turn a light on, Phil. You're disappearing on.
He's the treasurer.
I know it is dark in here. I'm sorry.
Were you sleeping?
No, I think I'm ready. I'm an impatient guy. I'm ready to do the auction and make it an auction right now.
Well, you guys want to vote on it?
And
The
the
majority
people that
win?
benefit, it's the benefit of being here.
Hey, Phil, as treasurer, you should be trying to maximize your return there.
Yeah, exactly.
Well, I don't think a silent auction is going to do it.
All right. Well, how many people of favor of doing it now?
I think
Raise your
Dennis put in a bid. so
Okay, if we like to do it. One thing, if you do it now, Phil will have the information, he can write a letter of acknowledgement to
Yeah.
Claire Fox, who donated these to us.
Do I have a motion to do it now? Bill,
Okay, I'll make a motion to do it.
is there a second in the house?
Second.
Yeah.
There is-
All right, let's have a acknowledgement. Is there any opposition against it?
I think you might get more money on the silent side.
All right. Anybody else wants to say something before we call the vote? Crickets? All right.
Even if you weren't in such a hurry, you could leave them out at the observatory at a couple Saturday night star parties and see if there's any interest from the public. Say these are available, make offer, whatever type thing. But that's just, whatever.
Well, then, if you want to do that, vote against. There's nothing bad anybody wants to vote for or against. That's not a problem. I'm just trying to see what the will of the people are. I'm trying to be democratic, I guess.
Why don't we wait until the board meeting?
Was everybody here in the board meeting? Pretty much, huh?
Just about, I think, but I say get rid of them now.
Well, we have a motion. Do we want to kill the motion or?
I'll withdraw the motion.
Okay, we got the motion withdrawn. We'll bring it up. Well, I'm kind of flip-flopping. I'm getting as bad as the politicians.
Well, if you really want to get into it, we can get rid of those, try and get rid of the eyepieces too that I listed. If anybody wants to bid on them things.
Did you send that out? Did you send that out yet, or am I just blind?
No, I sent out one a long time ago, the Excel spreadsheet of all the eyepieces we have.
You might want to refresh our memory.
Well, I can send
sometime.
out a list of them.
All right.
I'll take the ones that are in the orange box, not the ones we normally use, and not even list them. But, I mean, we got a whole bunch of them that were donated or whatever to the club, and we need to, they're just sitting there. Nobody's going to use them. So if anybody wants, $5 a eyepiece or something, eventually, or silent bid on them. I don't know if you want to.
Why don't we discuss all this next week at the board meeting?
Yeah, that's kind of, all right. Anybody opposed to that?
Nope.
No?
We had, what, 23 people here?
Yeah, we don't have that many now.
We don't get that much very often, so that's.
You had an excellent
It's one
speaker
time.
tonight, Phil.
Huh?
You had an excellent program tonight.
Yeah.
Yes, we did.
That's right, we did.
We did. You got the record for running a speech across the meeting, I think. But it was all good.
Sorry, I dragged on.
No, you did a great job. A lot of work.
I didn't want to go into auction mode and try and get it done.
Yeah, that's why I didn't
Wouldn't have
go
worked.
into that. All righty.
Julie, make sure you include Geddes on the binocular thing, because he's actually expressed interest
Geddes, you still there with us?
at the board meeting.
Yes, I am.
You want to be invited to the next board meeting so you have a chance?
Sure.
All right, we'll let you come and go as you please. So I'll make a note to put you back on the list temporarily, and and I'll leave you. But if you don't want to, that's good. I can put you in, put you out. All right.
I'll send out a list of the eyepieces again. It's in Excel, so.
Okay. What do you say we call this an end of the meeting, huh?
End of the meeting.
I'm good for that.
All righty. Everybody, thanks again, Joe. That was a very well done, technical, and by the points there. We appreciate the discussion too, and all the good stuff you guys brought up.
That was fun.
Yeah, you're leaving
All
us
right.
with some interesting things to wonder about.
Yeah.
Light bulb.
Whether my filters are any good.
Yeah, you with that light bulb, you're kind of chasing a dinosaur, aren't you? All right. I'm gonna sign off myself, but if anybody, I don't know if somebody wants to go on, but I've had enough.
Me too. Good night, all.
Good night, everybody.
Good night.
Bye.
All right.
Good night, Julie.
Okay.